Hello, good morning, good evening, good afternoon, everyone, wherever you might be. It is my great pleasure to introduce, for a change, somebody from Odense, our fourth speaker from Denmark, Jens KAAD. He will speak about group cocycles on loop groups, and this is joint work with Richard Nest, who will take over from him at the end of this talk, and Jesse Wolfson. Jens, for the time being, the floor is yours. Take it away.
Thanks a lot, Piotr. So thanks a lot for inviting me to give this talk. It's a real pleasure and honor to be able to speak on this occasion. So as Piotr said, it's a little bit special talk because I have to leave before 6:30. But Richard Nest, who is also a co-author on this paper, has agreed to take over and then answer any questions that you might have once the talk is over. So I hope he is indeed coming.
Yeah, he is already in here. Yes.
Okay, excellent. Okay, so anyway, as I said, this talk it's based on joint work together with Richard Nest and Jesse Wolfson. And what we have been doing is that we have been constructing higher central extensions of smooth double loop groups. And these higher central extensions, they give rise to cohomology classes in degree 3 on the smooth double loop group. And we've been able to check also via explicit computations that these cohomology classes can be non-trivial. So in order to construct these higher central extensions, we are combining methods from two quite different worlds. So one of them is noncommutative geometry and operator theory, and the other one is a higher category theory. Okay, but I thought that in order to explain and motivate these results, I would perhaps start out by just talking about what happens for smooth loop groups instead of smooth double loop groups. And I'll start out with a quite basic construction called a tame symbol. So now I will share my whiteboard. Okay, so what is this tame symbol? If I can write it. So here you start with two continuous functions on the closed unit disk, okay, and then you suppose that if I restrict them to the boundary circle, then they are elements in the smooth loop group. So when you restrict them to the boundary circle, they are smooth and invertible. Okay, and then one more thing, when you restrict them to the interior, so to the open disk, then these two functions become holomorphic. Okay. So then you can look at their set of zeros. So you have the union of the zeros for F and the zeros for G. And if I have such a singularity, then it has some order. So this F has an order at this point. It's a positive integer, and also G has an order at this point. And so if this order is equal to 0, it means that lambda is actually not a 0 for F. But otherwise, it's a strictly positive integer. Okay, now I would like to make sense of what happens to the quotient. So now I look at F divided by G, and I would like to see what happens to this quotient as my parameter approaches this singularity lambda. So a priori, this limit does not exist, but if I raise the numerator to power, which is the order of the 0 for G, and I raise the denominator to another power, which is the order of the 0 for F, and then I let Z approach lambda, then this limit here, it does in fact exist. And okay, I can also multiply it with a sign, namely the sign given by the product of these two orders.
Sorry, probably this lambda should belong to the intersection, not to the union, yes?
No, I actually mean the union. So it's okay if lambda is not a 0 for F, actually.
So in this case, m lambda is 0, yes?
Then m lambda of F is 0
Okay.
down here, and then you get 1 in the denominator.
Okay,
Okay,
so that's fine.
Yeah, yeah. So I really mean the union here. Okay, and this limit here then exists, and it's actually what is called the local tame symbol of these two functions at this singularity. And then, since this set of zeros here, it's actually finite, then I can look at the product of all these local tame symbols. And that will be my tame symbol for these two functions. Okay, so that's just
a stupid question. Why is it finite?
Because which one is? So this set is finite because they are invertible on the boundary circle and holomorphic on the interior.
Okay.
So then there can only be finitely many zeros.
Yeah, yeah.
Yeah. Okay. So I take the product of all these local tame symbols, I get my tame symbol. Okay, and it's an invertible complex number. Okay, so this quantity here, it's linked to the topic of this talk by means of a central extension. And that's the central extension of the smooth loop group. And I think that the correct way of introducing this central extension is by using operator theoretic techniques. So that comes here. Okay, so now we look just at a group of invertible operators on a separable Hilbert space. So we have a representation of this group. It need not be unitary, they're just invertible bounded operators. And then we have a projection on this Hilbert space, and we say that this is a polarization of this group. It means that when I look at commutators between this projection and group elements, and I get a trace class operator. Okay, and so it's a compact operator. If I look at the eigenvalues of the absolute value, they form a one-summable sequence. Once I have such a polarized group, I can write down a central extension of this group, and this central extension it appears in many places. I found it in the book Loop Groups by Presley and Siegel. So once you have such a polarized group, you can write down a central extension of this group by the complex multiplicative group. And then we know from the general theory of central extensions that such a central extension gives rise to a cohomology class in degree 2 on this group with values in the complex multiplicative group. Okay, so let's go back and see what this has to do with my tame symbol. So let's see. So now, if I look at the smooth loop group, This will now be my group G. So this will be the smooth functions from the circle to the complex multiplicative group. And then I want to define a polarization of this group. So first of all, I need to represent it on a Hilbert space. Well, the Hilbert space will be L2 functions on the circle. Okay, and then I have a representation actually of the ring of smooth functions on this Hilbert space. It acts there by multiplication, left multiplication, and so since this smooth loop group is nothing but the invertible elements in this unital ring here, I also can think of G as acting as invertible bounded operators on this Hilbert space. So that was the first part of my polarization. And then the other part is this projection. This will be the projection onto Hardy space. So P will just be the projection onto Hardy space. So the image of P here will be the Hardy space. So this will be all the L2 functions where all the Fourier coefficients with a strictly negative index is equal to 0. Okay, and then one can check that this polarization or this projection here provides me with a polarization of this smooth loop group. Okay, so this gives me a polarization. Hence, we know that we have this Presley-Segal central extension. Hence, we have this cohomology class in degree 2 on this smooth loop groups. Okay, so on the other hand, I can look at my two functions, f and g, which I started out with these continuous functions on the closed unit disk, and I can restrict them to the boundary circle. I get elements in this smooth loop group. So I can look at actually a homology class, which comes from the restriction of these two functions to the boundary circle. This will just be a commutator. This is the class given by this formal commutator here. So this gives me a class in group homology with integer coefficients. And so I can pair this class in group homology with this class in group cohomology. I get an invertible complex number. Okay, so if I do that, I can try to find out what is this invertible complex number. That's exactly my Thames symbol. Okay, so that's how this Thames symbol links to central extensions of smooth loop groups. Okay. So now I can try to formulate the main question for this talk. So what happens if we try to replace this smooth loop group with the smooth double loop group? So if I instead look at instead of looking at smooth functions from the circle to the invertible complex numbers, I look at the smooth function from the two torus to the invertible complex numbers. Can I then build a kind of higher central extension of this smooth double loop group. And I should say that if we are in a slightly different world, so if we replace this smooth double loop group with the formal double loop group, so if we, instead of looking at smooth functions on the two torus, we look at formal Lorentz series in two variables, then there is a satisfactory answer to this question, and it's due to several people. I should here mention Frankel and Ju, and Kocycles and Osipov, and Browning, Grosjenik, and also my collaborator, Jesse Wolfson. So this answer to this question includes construction of higher tame symbols and their relationship with group cohomology and higher category theory and algebraic K-theory also. This little change when you replace the formal double loop group with a smooth double loop group could seem fairly innocent at first sight, but in reality, when you start treating the smooth double loop group instead of the formal double loop group, there's a whole range of new analytic questions which you cannot see when you're working with the formal double loop group. And one of the main differences is that when you treat the formal double loop group, you can work entirely with vector spaces and finite rank operators. But when you have to treat the smooth double loop group, you have to work with Hilbert spaces and trace class operators in a systematic way. And this is quite difficult to align with concepts from higher category theory. But let's see what happens.
I have a question.
Yeah.
So in this formal setting, what is the replacement of the Hardy space?
There is no replacement of the Hardy space.
There is no.
No, not really. I mean, and I think that when we come further in this talk, you might get an answer to your question. So, yeah.
Okay.
So I hope that you will get an answer later on. Essentially, one has to work with, with two different projections instead of a single one. But you will see it, I think. Okay.
Sorry, this fact that you have to deal with two projections is not due to this formality, but it is due to the fact that we now deal with double loop groups, yes?
Yes, yes, yes.
But this formality has a consequence, as far as I understood, that instead of trace class, we have finite rank, yes?
Yeah.
Okay.
It's a much longer story than what I'm saying just now. It's fairly complicated what happens, and I hope I can give some idea of it when the talk progresses, because it's not just working with trace class instead of finite rank. It's it's actually much worse.
Okay.
Yeah. Okay, I'm still not going to attack this smooth double loop group. I'm going to spend even more time talking about the smooth loop group, just because I would like to explain how you can construct this group cohomology class coming from the Presley-Siegel central extension, how to construct it using groups acting on categories. So to this end, I will need a result of Kulinski. Actually, so Kulinski's theorem tells us how to construct group cohomology classes from groups acting on categories. So his theorem actually works and creates generality than what I'm going to state now, but we have fine-tuned it to the setting we are interested in. And this setting is as follows. So we work with what is called a connected category of lines. So we have some small category with at least one object, okay? And then this is a connected category of lines. This means that all objects are isomorphic, so it's connected. And then this category is enriched over vector space over the complex numbers. So this means that whenever I have two objects, then the morphisms between them form a vector space over the complex numbers, and composition is bilinear. And then the last condition is that it's a category of lines. So this can be formulated as follows. Whenever I fix an object in my category, then the endomorphisms of this object will be a vector space. And this vector space is isomorphic to the complex numbers in a canonical way, namely it sends unit to the unit to the identity morphism. So this has as a consequence that whenever I look at two objects, x and y, then the morphisms from x to y will form a one-dimensional vector space, so a complex line. So the morphisms from x to y will be isomorphic to the complex numbers, but not in a canonical way. So because such an isomorphism depends on the choice of a basis vector. Okay, if you are in this context and you have a group acting on such a connected category of lines, so if you have a strict action of a group on such a connected category of lines, then you can write down a group cohomology class in degree 2 for this group, and it takes values in the complex multiplicative group. So the first task which I'm going to do here is that I would like to explain that how, if I'm given a polarized group, how can I then construct such a connected category of lines with an action of this polarized group? How can I do that? And can I use, so if I'm able to do that, then I would get such a cohomology class in degree 2. And I would like to show that this cohomology class in degree 2 is the same as the class coming from the Presley-Siegel central extension. So I'm now going to start with a polarized group, and then I'll construct one of these connected categories of lines out of it. And to this end, I'm going to use operator theory. So I'm going to use graded determinant lines for Fredholm operators. So let's see how that goes. So here's this concept. So you have now a Fredholm operator acting between two Hilbert spaces, and then I can associate a graded determinant line to this data. So it's a complex line together with a grading, which is an integer. So I have a Fredholm operator, so it has an index, dimension of the kernel minus dimension of the co-kernel. That will be the grading of my graded determinant line. But then I'm constantly carrying around an extra piece of information, namely the determinant of this Fredholm operator. This determinant is a one-dimensional complex vector space. So, and it's given by the top exterior power of the kernel tensor the dual of the top exterior power of the co-kernel. So that's my graded determinant line. And we know from theory of Fredholm operators that when I compose two Fredholm operators, then I get a new Fredholm operator, and the index will just be the sum of the indices for the two terms. There's an analog of this fact if you look at graded determinant lines, and this is known as the torsion isomorphism. So if I have two Fredholm operators which I can compose, then I can actually write down a canonical isomorphism between their graded determinant lines. This is called the torsion isomorphism. So it's an isomorphism between the tensor product of the graded determinant lines for T and S and the graded determinant line for their product. So it's a torsion isomorphism. Now, we also know that if we take a Fredholm operator and perturb it by a compact operator, you get another Fredholm operator and the index doesn't change. So the index is invariant under compact perturbations. If we are working with graded determinant lines, then there's no direct analog of this invariance under compact perturbations. In order to get a canonical isomorphism between graded determinant lines, you will need to know that your perturbation is of trace class. But in this case, there's a construction due to Richard Carey and Joel Pinkus. Says that if you have two Fredholm operators acting between the same Hilbert spaces, and you know that their difference is of trace class, then you can actually write down a canonical isomorphism between their graded determinant lines. This is called the Kerrypinkus perturbation isomorphism. And I think this construction is perhaps not so familiar to people. So I wanted to spend some time just explaining what it looks like when T and S are both invertible, actually. So if T and S are both invertible, then there's no kernel and no co-kernel. So the index will be trivial, and the determinant lines will both be equal to the complex numbers. So in this case, we're looking at an automorphism of the complex numbers. This will be an invertible complex number. And this invertible complex number is something more familiar. This is the Fredholm determinant of their quotient. So, and here you really see why is it important that T minus S is of a trace class, because if I want to apply the Fredholm determinant to this quotient, then I better know that this quotient is of determinant class. So I need to know that it's a trace class perturbation of the identity operator. And that's exactly the same as saying that this difference is of trace class. Okay, once you know that this quotient is of determinant class, then you can write down this Fredholm determinant. I can choose a logarithm of this quotient, which is of trace class, apply the operator trace and the exponential function. And that's what this perturbation isomorphism looks like in this special case. But it does make sense also when T and S has non-trivial kernels and co-kernels.
Sorry, could we go back to the previous slide?
Yes.
So at this moment, do you define what does it mean for two determinant line bundles to be isomorphic? It just means that the data is the same, or there is some kind of canonical morphism?
Yeah, so it means that the two lines, the two one-dimensional vector spaces are isomorphic, and that the grading is the same.
But abstractly,
that's what it means. I can say what it means for two one-dimensional complex vector spaces to have an isomorphism between them.
Yes, but I mean abstractly. Yes, you have this absolute value of T as this determinant line bundle just consists. If we look up to isomorphism classes, it consists.
It's not up to isomorphism. It's very important that you do not just identify this with the complex numbers. Okay.
Yes, but yes, I suspect that, but I'm not seeing where this information is hidden. It is carried by what? Not by index.
It's the arrow that carries this information, right? You have two one-dimensional vector spaces. You know what's their product. That's a product. It's another one-dimensional vector space. And then you have a linear map from that to another one-dimensional vector space.
Mm-hmm.
But that's the construction, right? It's functorial construction.
Okay, so you view this as a morphism, and then this lemma somehow explains what does it mean that we have a morphism between two such objects, and then isomorphism is understood in the categorical way.
No. It's you know exactly what it means to have an isomorphism between two graded determinant lines. It's an isomorphism between the two one-dimensional vector spaces. Okay, and the grading has to be the same. That's exactly what it means.
Yes, but I'm very confused by this answer, since the isomorphism class of a vector space is just a number. This is just a dimension. So you have two numbers. In fact, this is a pair of numbers. One positive and one integer.
No, you have vector spaces. You have two one-dimensional vector spaces. No numbers. Two one-dimensional vector spaces.
One, yes, exactly. One-dimensional.
Just vector spaces, right? Without basis, you don't have a basis. Just vector space, right? Two one-dimensional vector spaces, and there is one constructs an isomorphism of both. There's a canonical construction given T and S. There's a canonical construction which gives you a map from tensor product T tensor S of two one-dimensional vector spaces to the third one-dimensional vector space determinant of ST.
So there's much more information in a
I have a question about this.
So somehow this lemma explains what does it mean to be isomorphic, yes?
No, you know, there's the word canonical in this lemma, right? Canonical isomorphism. In general, if you have two one-dimensional vector spaces, there is no canonical isomorphism. There are tons of isomorphisms, right?
Okay.
This lemma says there is a canonical one. So factorial in T and S. Paul, sorry.
Paul, go ahead.
Well, I have a question about this definition that I'm seeing on my screen. But the determinant of T is a Fredholm operator, all right? Determinant of T is a certain one, you have it quite precisely. It's a one-dimensional vector space. But how do you read this then? This what absolute value of T? I don't know how you read that.
Okay, so this absolute value is given by this pair.
What do you mean by that pair? What does that mean? Are you thinking of index of T as a number? Is index of T? It's usually a number.
That's a number. That's just a grading.
So what do you mean by that? What is it's given by a pair consisting of a one-dimensional vector space
and
a number.
An integer.
So it's a one-dimensional vector space together with an integer.
Yes.
Right. And what is the grading? You say the graded. What is the grading?
A set graded line is just a line together with an integer.
A line, you mean a one-dimensional vector space?
Exactly.
Okay.
And
so we are talking about a certain
this integer. Yeah.
So we are talking about a certain one-dimensional vector space, which is very precisely indicated, together with a given integer.
Exactly.
Which can be positive, negative, or zero.
That's it.
Okay. Well, then dilemma has to do with the composition of Fredholm operators, basically, right?
Yes, but it says that this tensor product of one-dimensional vector spaces I have here on the left-hand side can be identified in a canonical fashion.
Yes.
With the one-dimensional vector space coming from the product.
Okay.
So it says more than just index of S times T is index of T plus index of S.
How exactly do you take care of the grading when you take this tensor product?
The gradings will be summed.
Summed, okay.
So the grading over here is index of T plus index of S.
Okay. Yeah.
Oh, I see. So you are working towards a category, I think is the point here.
I'm working towards the category. That's right.
Yeah, you are progressing towards a category. Yeah, okay, good. Okay, all right, very good, very good. Okay, thank you.
Okay, no problem. I will continue. So here's also this perturbation isomorphism. I have been talking about that too. So hidden here is that the indices are the same but there's much more to it. I'm also identifying these complex lines coming from T and the one coming from S in a canonical fashion. Okay, this I talked about. So now comes this category that you were predicting, Paul. So now I start with my polarization of this group, and then I write down what I call the determinant category. So this category has some objects. This will just be the group G. And then whenever I have two objects, I need to specify what are the morphisms from G to H. The morphisms from G to H will be one of these great determinant lines. So this is going to be the great determinant line of a particular Fredholm operator, namely a product of two idempotents. It can conjugate P with G and it can conjugate P with H. And this product of idempotents will be a Fredholm operator because P polarizes this group. So commutators between P and group elements are of trace class. So this will be invertible modulo compact operators. In fact, modulo trace class operators, but so those are the morphisms. And now comes the composition of morphisms. So the composition of morphisms uses this torsion isomorphism and the Kerrypinkus perturbation isomorphism. And I would like to show you how. So that comes here. Okay, so let's see. So this composition, how does it go? So we now look at morphisms from G to H, tensor morphisms from H to K, and I want to end up in the morphisms from G to K. That's my composition. It's going to be bilinear. That's why I'm writing tensor product. Okay, so here on the left-hand side, I have tensor product of two greater determinant lines, namely the one from HPH inverse times GPG inverse, tensor the one from KPK inverse times HPH inverse. And these two Fredholm operators, they are composable. So I have my torsion isomorphism. So I end up in the great determinant line for their product. KPK inverse times HPH inverse. I'm not repeating this because it's an idempotent. GPT inverse. Okay, I want to end up in the morphism from G to K. So this will be greater determinant line for KPK inverse times GPG inverse. So these two lines are not really the same because I have this extra term in the middle. But since I have a polarization of this group, I know that commutators between P and group elements is a trace class. So these two Fredholm operators, they will agree up to a trace class operator. So therefore I have this perturbation isomorphism. And that's the composition in my category. It's torsion composed with perturbation. And okay, then you have to work. You have to work quite a lot in order to prove that this composition is associative. But it can be done, and you have even more. You have that this determinant category becomes one of these connected categories of lines, and the polarized group acts on this category in a strict fashion. So on objects, it acts via left multiplication, and on morphisms, you act via conjugation. I'm not going to specify exactly how, but it can be written down. This action. Okay, so from my polarized group, I construct this determinant category, which is a connected category of lines with an action of this polarized group. So I can use the theorem by Kulinski. Kulinski's theorem says that when I have one of these connected categories of lines with a group action, I get a cohomology class in degree 2 on this group. And So my determinant category here gives rise to this commodity class via Kulinski's construction. And we can then prove, this is the first main result of this talk, that this commodity class coming from this determinant category agrees with the commodity class coming from the Presley-Siegel central extension of my polarized group. And here again, I have a comment on the algebraic setting. So if you are in the algebraic case, so if you replace this Hilbert space H by a vector space, and you essentially replace trace class operators by finite rank operators, or you work with finite dimensional subspaces of your Hilbert space, then there are similar results available by Arborello, De Concini, and Katz. But again, in this analytic setting with Hilbert spaces and trace class operators, there are many convergence questions that you have to deal with, and you cannot see them in this algebraic setting. So this ends the first part of this talk. So now I'm going to start talking about the smooth double loop group instead of the smooth loop group. And I'll start by introducing the analog of this polarization of a group. So I'll try to introduce an analog of this concept which works for the smooth double loop group instead of the smooth loop group. And this will be what we call a bipolarization of a group. So that comes here. So we still have a group of invertible operators acting on a separable Hilbert space. And then instead of a single projection, we use two projections, P1 and P2. And they will form a bipolarization of this group when there are two conditions that are satisfied. The first one says, so I can conjugate P1 with G and then take commutator with P2. This has to be of trace class. The other one says that if I take a commutator between P1 and a group element and multiply it with a commutator between P2 and a group element, this will also be of trace class. So we think of these P1, P2 as specifying kind of a vertical and a horizontal direction in the underlying geometry. But I will tell you what it looks like for the smooth double loop group.
Sorry, Jens, just a silly question. So I guess it follows that also the commutator between P1 and the conjugation of P2 is also trace class. You can just derive it, right?
Which one? Sorry.
Another commutator. Imagine that now you conjugate P2 instead of P1.
Oh yeah, over here. Yeah. It's symmetric in the two.
Yeah, you can just conjugate it, and this just follows. All right, just to make
sure. Exactly. So it looks like it's not, but it is symmetric.
Yeah, that's exactly what I expected. Okay, thanks.
Yeah. Okay. So let's see what happens for this smooth double loop group. Let's see what happens there. Okay, so for the smooth double loop group, so this will be smooth functions from the two torus with values in the complex multiplicative group. This will be my group G now, and I want to define a bipolarization of this group. Okay, so we have to represent it on a Hilbert space. It will be represented on L2 functions on the two torus. So Hilbert space. H will be L2 functions on the two torus. And this is, of course, isomorphic to the Hilbert space tensor product of L2 functions on the circle with itself. Okay, and then I have representation. Of the smooth functions on the two torus, this ring on this Hilbert space. It acts via left multiplication. Very good. So this group is just the invertible elements in this ring. So in this unital ring, so I also can think of T as sitting inside the invertible bounded operators on this Hilbert space. Very good. So now comes my bipolarization. It's given by these two projections, P1. Okay, projections. P1 will be tensor product onto Hardy space tensor the identity, and P2 will be identity tensor projection onto Hardy space, and they will definitely act on this Hilbert space. So here we have again projection onto Hardy space. And one can verify that this gives me a bipolarization of this group. So this is a bipolarization. And there's just a little comment to this. So if you take one of these smooth double loops here, and you take commutator between P1 with P1 and this smooth double loop, then you will in general not get a compact operator at all, because it will look like trace class tensor bounded. Okay. So if you just take a group element and take commutator with P1, it's going to be a terrible operator. It's not even going to be compact. If I take commutator between one of these smooth double loops and P2, then I get something of the form bounded tensor trace class. Okay. So if I take the product of these two commutators, the one involving P1 and the one involving P2, I'll get trace class tensor bounded times bounded tensor trace class. This is trace class tensor trace class. That's going to be trace class. So that's why you have this condition here. Here, commutator of a group element with P1 multiplied with a commutator with a group element involving P2 is trace class. But if I just look at a single commutator here, it need not be compact at all. It's a combination of these two commutators that gives me something interesting. Okay, yeah. So the next thing we're going to do is I'm going to explain what kind of input from higher category theory I'm going to use in order to get group cohomology classes of degree 3 on such a bipolarized group. And I'm going to use groups acting on higher categories, and it has been known for quite a while, at least going back to the work of Ross Street, that you can use groups acting on higher categories to construct group cohomology classes. In particular,
I have a question?
Hmm?
Can I have a question here? What if you just compose P1 and P2 and take commutators with G? Is it an option here, or it's a stupid idea?
P1 times P2 commutator with G will give you nothing interesting. What you could do, okay, what you could do is that you could observe that P1 and P2, they are in fact coming from, I mean, the usual Fredholm module on for the smooth functions on the circle. So what this is kind of mimicking is actually their exterior Kasparov product.
Mm.
So what you could do if you want the relationship with something more familiar is that you could look at, you could apply Kasparov's technical theorem to P1 tensor 1 and 1 tensor P2, and you could get a class in k-homology for the continuous functions on the two torus.
Okay,
but
thanks.
just looking at their sum or their product will not give you anything. Yeah. I don't know whether that answered your question.
You did, thank you.
Okay, okay.
To some extent, I understood the answer, but not fully probably, but it's my ignorance.
So this
Don't try to fix it. Don't try to fix it. It was sufficient.
This kind of a definition is to mimic what you get if you take the Kasparov product of these two Fredholm modules without doing it.
Okay.
Yeah. Okay, so here comes, okay, I was telling a whole story. So, we're not really going to use groups acting on two categories, but a slightly different setting in order to get our group cohomology classes. And this setting is, I mean, it's dictated by our analytic examples. So instead of a two category, we're going to look at a family of categories, and these categories appearing in my family, they're going to be linked together by various coproduct functors. And moreover, since I'm really interested in group cohomology classes with values in the complex multiplicative group, I'm going to assume that all these categories appearing in my family, they're all connected categories of lines. So here comes the definition. So this is a definition of a coproduct category of lines. So it all takes place over a non-empty set X. Okay, and then whenever I have two elements in this set X, I have one of these connected categories of lines, h of x, y. So h of x, y is connected. It's enriched over vector space over the complex numbers, and the endomorphism vector space for any object alpha is isomorphic to the complex numbers in a canonical fashion. Okay, so I have a bunch of these connected categories of lines. And then they're linked together by functors. So whenever I have three elements in this set X, I actually have a functor which sends this category h of x, y to the tensor product of categories over here. H of x, z tensor h of z, y. So that's kind of a coproduct functor I have here. And these coproduct functors, they are required to satisfy the co-associativity law. So here if I have four elements in capital X, I have two ways of passing from this category in position x, y to the tensor product over here. I can either first insert z and then w, or I can first insert w and then z, and this should give me the same thing. So these two functors, they will have to agree as functors. So if you are familiar with two categories, then you will find this a little bit odd, because usually if you work with two categories, then the associativity law is only satisfied up to natural isomorphism. But okay, so I should maybe explain what the link is between such a coproduct category of lines and then a two category. So if you start out with one of these coproduct category of lines, then to get a two category, the objects in your two category will be this non-empty set X. And then whenever I have two objects, I want a category of morphisms from X to Y. This will be this connected category of lines, h of x, y. So those will be the morphisms from X to Y. It's a category of morphisms. And then I want to compose functors. So if I have three objects, I actually need a functor going from this tensor product and down to this domain of my coproduct functor. It turns out that all these coproduct functors are equivalences of categories. This can be proved. So I can invert them up to natural isomorphism. So when I invert these coproduct functors, I get the composition in my two category. But since there are many choices involved in such, when you invert such a functor up to natural isomorphism, then the associativity law in my 2 category will only be satisfied up to natural isomorphism. So now comes the second main result of this talk. So it says that if I have one of these coproduct category of lines and I have a group acting strictly on this data, then I can write down a cohomology class on this group in degree 3. And it takes values in this complex multiplicative group. So whenever I have a coproduct category of lines with a group action, I have a cohomology class in degree 3 on the group which acts on this categorical data. And the third main result says that if I now have a group of invertible operators on a Hilbert space together with such a bipolarization, which we saw earlier what this means, then we have a method for writing down such a coproduct category of lines together with a strict action of this bipolarized group. In particular, we get from this coproduct category of lines a cohomology class in degree 3 on this bipolarized group, and it takes values in the complex multiplicative group. Now you could say, Jens, are you not just talking about something trivial here? Could it not happen that this cohomology class was always just trivial? And in fact, so we saw earlier that when I have this smooth double loop group, we saw how to construct a bipolarization of this smooth double loop group. So this theorem applies to the smooth double loop group. So we get a cohomology class in degree 3 on the smooth double loop group with values in the complex multiplicative group. And we could prove by explicit computations that this cohomology class that we get on the smooth double loop group is in fact non-trivial. So I think that was everything I wanted to say. So thank you very much for listening.
Okay, thank you so much. It's not the end of the talk, but this is when we switch gears, okay? And Jens, before you go, first, maybe somebody still has some questions which are designed especially for you.
Yeah. I mean, I just have to go in like 10 minutes or something like that, so I can stay for another 10 minutes.
Okay, you can stay for another 10 minutes. So any questions for Jens before Richard takes over?
I have one, and it may be a little weird and trivial. Way back in the single loop groups, when you defined the modulus of T as a pair determinant of T and index of T,
yes,
then multiple times there appeared the tensor product between two of them. Is it just a notational convenience, or do these assignment of assigning the tensor product of the one-dimensional spaces and the sum of those numbers, does it satisfy the definition of a tensor product, or is it denoted as a tensor product simply because we take tensor product of debts and indexes? Well, we just add them, and this is the reason.
So you have two things, right?
Yes, I have a one-dimensional space debt, and I have the number index, right?
This means also a line and a number. Yeah. The line is given by the tensor product of the lines for T and modulus, and the number will be the sum of the two numbers.
Okay.
I guess you're asking there's some universal property which normally defines the tensor product.
Is there the universal property that would justify the denoting the action on this pair by the symbol, or is it just because we applied on the first coordinate?
Mhm.
Well, I mean,
Thank you very much.
I think it obeys everything you want from a tensor product.
Mhm.
It's essentially just a tensor product of lines, and then you're keeping track of a little bit of extra data, namely a number,
Mhm.
which you're summing.
Adam?
Maybe very trivial question, but okay, so you are able to construct some class in the third cohomology group of this group cohomology, and this group is huge. So how much is known about this cohomology group in general? For example, is it known that without this construction that the third H3 of this G of C star is different from 0 without knowing this construction?
Good question. Good question. My my guess is yes, but then yeah, I mean I cannot really answer that question in a very satisfactory way.
But in general, this group is so huge that this cohomology is not expected to be known fully. Yes.
Yeah, I think that there could be plenty of things in there.
Do we know such things, for example, whether it is at least finitely generated, or even this is not known?
I actually really don't know. Perhaps someone else can answer this question. I know very little about this cohomology.
Because you see, the group cohomology is in fact this ordinary singular, for example, singular cohomology of the classifying space. And you start with something which is very small, like a circle. You get a classifying space. Sorry, not for a circle. I believe it is, but maybe for usually what happens. Usually, what happens is that you obtain something which is infinite dimensional, but it has a structure of a CW complex. So this is some kind of a limit of things which are finite dimensional, but this works for example, as far as I know, for Lie groups or maybe for discrete groups. But here the group is huge. It's the infinity of a circle, yes.
Yeah. So
it's already infinite dimensional.
It's very much related to the algebraic K-theory of the smooth functions on the two torus, the third algebraic K group.
The third one, yes.
Yeah. But I think Jonathan, did you have a question?
Yeah, good, Jonathan.
Yes. Okay. So I was just wondering, you talked here about the two torus and functions that extend to the polydisk. I mean, presumably you could do this with higher dimensional tori. Is there a similar construction in higher dimensions?
So that would be great. That would be great. It's a very good
you need tri-polarizations, etc.
Yeah. But it was. I mean, it's this. I mean, it takes not such a long time to state this theorem here, but constructing this coproduct category of lines was, at least for us, highly non-trivial. It took us a long time. Yeah. So
presumably you'd expect that for an n polarization, you should get a cohomology class and dimension n+1 or whatever.
Yeah, exactly. Yeah. And that's also, so I think the people who are doing it, I mean, for this in this formal setting, they already know how to do this.
Uh-huh.
Yeah, if you look at formal Lorentz series in variables, yeah. But there are some technicalities which are really difficult to overcome when you want to do it analytically. Yeah.
Okay, thanks.
Tomek?
I have one comment and one question.
Mm-hmm.
If you could come back to this tensor product of determinant line bundles. So the no,
I was here. So
it was
there.
Yes, this one, this torsion isomorphism. So the first question is maybe it's a rephrasing the first question of Adam. If they form a monoidal category, so this is the question of this natural transformation. Okay, between two functors. One functor goes from the monoid of Fredholm operators, and then it goes to the monoidal category of line bundles, or this line bundles plus indices. So the question is whether this could be interpreted as a monoidal functor transformation. Okay, it's not so about universal property of the tensor product, but it's a question about this natural transformation being a transformation of monoidal functors.
I would guess so. I mean, this is
I suspect this. It would be the best language to rephrase.
Yes.
It's associative.
So,
it has many nice properties.
Yeah. So this is the matter of commutativity of some diagrams to check. But my question, in fact, is about this what you called coproduct categories. So in some sources, such structures are called co-categories.
Okay.
My question is, what about this curly H of X, Y? Is the finite dimensional space?
Curly H of X, Y is a category.
It's a category, but don't you have an operation of a dual for such category of lines?
I would believe so. Yes. Yes.
Then this functor delta could be dualized to some composition. Of the dual of this co-category. Okay, something like this. And then the question is, what is the higher categorical status of this construction? Is the two-category, bi-category, gray category, or whatever from the higher category theory? Because after separating this product from a product, it's very hard to say what is the relationship between compositions and co-compositions on different levels. But maybe it's after this dualization, it would be something which is familiar to experts in higher category theory.
That could be. So there's, I mean, okay.
So the question is about this dual on the level of the connected category of lines. Can this be dualized?
I think one can do that. I cannot, but so that there's perhaps another answer with this, that you can, I mean, I also said this a little bit during the talk, that it turns out that all these coproduct functors are equivalences of categories. So you can invert them, and then you get an honest two category out of it.
Weak two category. Weak two category.
Weak two category.
Weak two category.
So by category, you mean?
No, weak two category composition is associated up to a two morphism.
So you only get the associativity law up to natural isomorphism.
But the rules of these compatibilities are different from coherences for by category?
No.
Ah, so it is simply by category. Okay, okay.
Yeah. But the point is that the reason why we are highlighting this framework here is that the co-associativity law is actually strict. Okay, whereas when you go when you pass to a 2 category, then the associativity law is only up to natural isomorphism.
Mm-hmm.
So somehow this context of this product category of lines is more natural for dealing with the examples we're having, because we get strict identity of functors, and we get strict action of our group also. So this is why it seems a little bit better to work in this context. But you can translate everything and get a 2 category out of it. Yeah.
So that's what you mean by strict action. But when you define it, mimicking the usual concept of an action, these identifications are actually strict. It's not just some natural transformations, right?
Yes. So the action that we get is actually an honest action. So it's not just that composition agrees up to natural isomorphism.
Okay, thank you.
All identities are identities.
On the nose,
On the nose. Yeah. So that's quite nice to work with.
Yeah.
Thank you.
Okay, anybody else? Well, if not, so just thank you again so much. Could you please send me your slides and also send me whatever you scribbled on whiteboard? Yeah, that's nice.
Okay.
You can save it before you kill your Zoom. You can just save it into PDF, and then I will, do the rest. Okay.
Yeah. I think I have it. Yeah.
Okay, and one more very important question: will your singing be available on YouTube?
No.
Such a shame. We would link it to this talk.
No. I wouldn't be so pleased with that.
Okay, so thank you again so much. Happy singing. And Richard, now the floor is yours. You take over.
Bye.
Bye.
Thank you,
Yes.
Bye.
I don't know. Do you have questions? Apparently, there are no more questions. So what?
Jens just answered my question about, I was wondering about strict action. Okay, I have a silly question about these co-product categories. So what's the general definition? I mean, not in the context of these lines and so on.
No, definition was so you have so you have objects. Morphism between objects form categories.
Okay.
So n2 objects X and Y, the morphism between those form a category.
Okay.
Right. And now in normal context, in normal context, you would take morphism between objects from X to Y, from Y to Z, and then you would compose them. Right, so you would have a map. You would have some natural transformation from product of these categories X, Y, comma Y, Z to X, Z.
Richard, are you sure you don't want to write? You don't want to write on?
It will be pretty hopeless if I try to write. Let's see. Can I?
Yeah, you can share the screen. It's
okay. Let's try this whiteboard. I have no idea.
Yeah, I see it perfectly well. Yes.
Yeah, but I don't know if I can write on it. Let's try. Right. So, so you have a given pair of objects X and Y. You have morphisms, right?
Yes.
From X to Y.
Correct. Yes.
And normal category means that you have a map from here, this times M Y comma Z. Sorry, Y.
Yeah.
Comma Z.
Yeah.
To M X Z. Right. And then satisfy some associativity condition.
Sure. Yes.
Now, what happens here is precisely the opposite one. Instead of that, you have. So morphism here means natural transformation because it's a morphism between two categories. So the arrows are natural transformations. Now what happens here, instead of having this natural transformation, you get a natural transformation the other way. And the co-associativity is in obvious sense the other way. Now these morphisms are actually equivalences of categories. So it's really something you have Picard category, so category of lines, tensor Picard category. This is again Picard category. So a kind of morphisms here are Picard category of lines. Morphisms here is also category of lines. And then you have, well, isomorph equivalence of these two categories. So you can invert it always. So you can always invert these natural transformations to other natural transformations. But once you do that, but as you were saying, the choice of the inverse is not unique. So once you do, because it's based on on the fact that your functor is equivalence of categories, not identity.
Exactly. Yeah.
Right? So once you invert it, your dual of co-associativity is associativity. Now your dual associativity will not be strict, meaning the composition, if you have three objects and then compose this way and this way, or you do it the other way around, right? So either 1, 2 or 2, 1. The two results are not the same.
Yes.
So these are two different natural transformation, let's say, of mx, z, right? So you get two different natural transformations. They're not the same, right? They are the same up to equivalence natural transformations. So in this sense, it becomes a weak two category. So morphisms form a category, which is necessary for, which is basic statement. I have a two category, but then the composition of morphisms should be a composition of morphism is a functor, but its functor should be associative. It's not. It's not associative on the nose. But if instead of it we use this coproduct thing, this you can write down explicitly, and this is co-associative on the nose.
Okay.
Okay.
But I apologize. It's a very silly question,
So
but I'm confused by this tensor product. By this tensor product, what does it mean like the tensor product? I need to have at least some abelian group structure, no? Or do you have
no, you have to one
thingy?
No. The tensor, all the tensor products are really between one-dimensional vector spaces.
In your special case, but in general?
In this case, in general, tensor, well, depends what category you are in. Here the category that we are in is the Picard category. Whenever there is tensor product showing up. It's really tensor product of two one-dimensional vector spaces. This is a one-dimensional vector space. Canonically.
What puzzled me when Jens wrote this tensor product, I understand it in your case, that you have a natural tensor product, but I would like to understand the general, concept of a coproduct category, and then I'm puzzled by what one means by the tensor product between two categories.
No, you have a tensor product between two categories. It's really a product between two categories. This tensor product part is because the morphisms have certain properties. So morphisms are vector spaces. So you tensor vector spaces.
Yeah.
Okay. So in this sense, otherwise you would do product, right? But it's a special situation where it's a linear. These are linear categories. So morphism spaces are vector spaces. So when you take a product of these two categories and you want to get a linear category, you have to tensor morphism spaces.
That's the answer.
As vector spaces.
Yeah,
right?
I'm happy.
That's all.
Yeah, I'm happy. Okay, anybody else?
Could I comment the last?
Sure. Go ahead.
Go ahead, Tomek.
Go ahead.
The problem is that what is involved here is something which is called enrichment. And this is in a sense, double enrichment. So this makes this situation complicated. So succinctly, the most succinct rephrasing of the structure is that it's a category enriched in the opposite of the monoidal category of categories of lines.
Now
So
I'm
from
completely
categorical
lost.
point of view, it could be not made shorter.
No.
So the situation is quite complicated. There are
It is
two steps
complicated.
enrichment, two-step enrichment.
Mhm.
And this tensor product, as Richard explained, is not a tensor product of categories. It is a tensor product in the monoidal category of enrichment of the first category, so, which are simply vector spaces. In fact, lines even. Homes between lines are
right?
lines.
Guys, do you know how I move this stupid whiteboard?
You can click on this cross here and then you go to the next page.
No. In which?
Well, what do you want? Do you want next page or what?
I wanted next page, but by now I don't have anything. I managed to click off everything.
Here, if you click on this plus, you will go to the next page. You see?
Okay, that's where it helps. Yeah.
Yeah.
But now I managed to get rid of.
No, if you go, you can always go back. I mean,
No, that's not the question. No, I managed somehow to get
your
rid
controls.
of control. Oh yeah, now I have it. Okay.
Okay.
Yeah. No, but maybe I'll show you something else, right? So, so the category itself. So it's really category enriched. So enriched. First of all, enriched over Picard category. So morphisms form Picard category, and then composition has this coproduct structure. So instead of defining composition of morphisms, you define co-composition, which is canonical. So, but maybe it's an answer why it's the answer to Adam why it's not quite accidental what we are doing, right? So a cocycle, right? So God knows what is a cocycle. So there is kind of background. I would try to. No, this is the wrong one. No, I think I. Let me just check if I can find it. Yeah, I think this one. Yeah. Okay, let me try to share some other. Stop share.
Yeah.
Share. Yeah, that one. Okay. Hopefully you can see something, right?
Yeah, we see, yes.
Good.
But it
So,
would be nice if you'd enlarge it a little bit.
Problem is that it's not really prepared for. No, sorry, once again. I'm not sure if I can make it larger. This was not supposed to be yeah, okay. Yeah, something like this. Try full screen. No, so the basic idea, so general is there is this picture here. So generally there is something called multiplicative churn character of Kohn and Karoubi, which you start with algebraic K-theory and a Samabu, appropriately Samabu Fredholm module, and you construct a morphism from algebraic K-theory to invertible numbers, so C mod Z. Now there is another construction for algebraic K-theory where you construct functionals on it, and there you take, there is a natural map from algebraic K-theory to group homology of an invertible group of elements in A, or matrices over A. It's called the Karoubi regulator. It's kind of natural map. And then even that.
Your screen?
Sorry?
Do we supposed to see your screen?
Can you see it or not?
No, we don't.
We at least myself, I don't.
No, we don't see your screen.
You don't see my screen.
No.
Share screen. Let's try again. Share. Well, now you can see it.
Yes.
Yes.
Yes, now we can see, yes.
Yeah, problems is very small, right?
Mm-hmm. Yeah, but oh, it's better now. Yes. Mm-hmm.
Maybe better, right? So
Yeah.
can I move it somewhat? Yeah. It's
Mhm.
right. It's not easy to
Yeah,
arrange,
but,
right?
but
So
we see now it's very
yeah.
nice.
So think about K2. So we think
Okay.
about circle. These functions about the circle, right? There's this natural Fredholm module on the circle, which is given by
Mhm.
Kepler's extension, or d by dz. And now this Fredholm module defines a map from K2 algebraic to invertible complex numbers. So there's this Conca-Ruby construction of multiplicative Chern character. On the other hand, there's this there is a formula which, in general, there's a map from algebraic K theory to corresponding group homology. So you look at the invertible elements in your algebra, it's smooth parts of the circle, look at infinite matrices and look at invertible infinite matrices. And then you take its group homology. And in general, from Kn algebraic to Hn. Now, in this case of a circle, there is this Fredholm module which maps, which is actually one summable, actually finite rank on top of it, which maps a K2 algebraic to invertible numbers. On the other hand, this Cocycle that Jens was constructed. So that on the other hand, there's this Karoubi regulator which goes from algebraic K theory to group homology. Now this Cocycle that Jens describes gives a functional on this bit on group homology.
Mhm.
So we get together we get this arrow from algebraic K theory to invertible numbers.
Mhm.
It's not nice, okay?
Mhm.
So that's what he was contracting. He described that that's this universal central extension construction. On the other hand, there is actually another regulator on the C infinity of T, something called Beilinson regulator. It comes from analytic theorem, well, algebraic geometry actually. So here it's about analytic curves, and it goes like this. So given two, and goes like this. So given two invertible elements, you can construct an element of K2, and then value of this regulator on the corresponding element is given by this formula here. So you take log, so F and G are invertible elements on C infinity of a circle.
Mhm.
Take log F, D log G. It's a one form and has a residue. It's a one form on the circle and such it has a residue. So you compute this residue and take its exponential.
Mhm.
So that's this Cocycle. And that turns out that this is this Cocycle. So this is actually part of a proof that, so in particular that this universal central extension actually really coincides with this Beilinson regulator. Now when you go to, I should have it here, right? Yeah. To circle, right? So now, so here the problems start. Sorry, for the two circle, you would expect the following. So two circles, so you would get something in K3 algebraic, product of three elements, and there is this Conca-Ruby regulator, Conca-Ruby multiplicative Chern character, which ends up in complex numbers from here to here. Again, there is this Karoubi construction, which produces element of group homology. And then we have a Cocycle. This Cocycle, which was very hard to construct, which goes from here to here. So the C here, which goes from group homology to complex numbers, invertible complex numbers. And now a kind of conjecture is that the two things coincide. So here I wrote down the formula. Here's the formula for actually for Beilinson regulator. So now you take log F, D log G. Actually, it's log F, D log G, D log H. And you take residue of log F, D log G, D log H. This looks more complicated because you have to be careful how you compute this residue. That's basically residue of log f, d log g, d log h. You see, and we did prove this actually on a big class of elements of synthetity of T2. It would be interesting to know if it is the same or not. Actually, hopefully it is the same. You see, because in general, it's not at all obvious that this multiplicative chain character, so this going, sorry, I can't really show it, can I? Or maybe I can annotate. Wait a second.
I can.
Well, let me try. Oh, no, I can't do it now because I have to change preferences in the secret computer. Select, no, no, I would have to change preferences. It does not want to let me, I'm afraid.
Mm-hmm.
So there's this map from K3 to C star, that's one which is actually due to Konkarubi. So there is a two-summable Fredholm module, which is really given by product of Kasparov, external Kasparov product, as he was saying. So there is this map from K3 to complex numbers. And actually, it's kind of conjecture that these multiplicative chain characters factor through this one in general. So factors through Karubi regulators, through group homology. So it's true for some subgroups of elements here, but we don't know in general. So actually, it's not quite accidental, but the way we get this. First of all, it's not accidental the way that we get this particular free cocycle. Actually, what would be interesting, something else, because this multiplicative chain character actually comes anytime there is a, what is it, two-summable Fredholm module on the algebra, on this algebra. So say Dirac operator for that matter. So anytime you have two-summable Fredholm module, you get a map from algebraic K-theory, K3 to non-zero complex numbers. On the other hand, the only way we manage to construct cocycle is via this double loop extension, right? So it's for a particular Fredholm module, which is a exterior product of Teplitz extensions. And then, of course, as he was saying, it will be interesting what happens for Kn, for Nan, right? So this map from Kn to C star. So it exists in the algebraic context, but it's not set. It's really this formula here. It's just generalization of Bielenson formula. So the map is, so you think this formal disk. So you think of formal N disk as what's called N-Tate space. So say Laurent series in N variables. And then you look at invertible Laurent series in N variables, and you look at K-theory, Kn of this one. And then there is this residue construction that's really here, which goes down to invertible complex numbers. So the one he was saying that exists, it's really this residue construction that exists. And for Laurent series, actually, you know that the residue is an isomorphism from Kn to Kn minus 1. So on formal disk, there is nothing else. On formal N disk, there is this corresponding class from Kn, on Kn, which is given by residue, on formal disk. On non-formal disk, so on the already on synthet of T2, that's not true. There's a lot of things in both K-homology, sorry, in both algebraic K-theory and group homology. So you get much more interesting element, much more information here. For smooth function of the two torus already, you get much more. Also, you can use, so this construction is kind of functorial. So it's really, So he didn't say that. He didn't explain how you construct these categories. But the way you construct these categories is it's kind of it's a clever way of writing down Kasparov pairing between K homology and K theory. So you choose an explicit way of writing the pairing. So instead of getting a number, you get a Fredholm operator. And you take it, so instead of taking its trace, you take its determinant. Okay, so these categories, these hop-like categories of lines is really, you really write down carefully pairing between K theory and K homology, not in terms of not homotopy invariant, but very concrete Fredholm operator. Let me see, can I think I have example of what you do. Yeah, actually this one here. So this one. So remember these projections he was talking about, this P conjugate by U and V. Here it's conjugated by, let's think of them as conjugated by lambda and mu.
With polarizations, right?
Yeah, these polarizations, right?
Okay.
Okay, and so here, so with one polarization, say so just one of them, right? And conjugate by group elements. So you write down this matrix. It's squares actually. It is actually squares and idempotent. Okay, and it actually defines certain class in some class of K homology somewhere, and then you hit it with okay, there's the whole structure, but so these P lambda, P mu are given by P1, one of these two projections. And then these pi, these representations, are given by the other projection. So, so this other projection produces this idempotent. So you put them around your omega, and then you get something which is Fredholm. So it's really pairing. Did I write it down somewhere? Maybe I did. No, I'm not sure. No, not here. I think that it is somewhere. No. Oh yeah. Yeah. Okay, that's actually the one. It's actually this one here. So imagine that you have a ring R and some subring. Sorry, ideal. And look at this extension. Okay. So given this extension, so fine. How do I do this? Yeah. So on top of this extension, we have a bunch of representations of of R. Okay, so we have a bunch of representations of this ring, which satisfy some L1 conditions, some summability conditions. But these summability conditions that he wrote before. So now what you do is the following. So pick up, so it's remember these pi lambdas representations of the ring R. So pick up images on the pi lambda, pi mu of a unit. So these are our projections. So these really think of those really these projections conjugated by group elements. And then you write down this matrix. Okay, so this is really boundary map. So the point is that P lambda, P mu, the point is that this is Fredholm operator. So you can write down the boundary map. You can write down boundary map from K1 here to K0 here. And that's the image of this boundary map. So that's an element K0 by ideal. And then, you look at this one, that's invertible modulo ideal. and think of omega symmetry on the boundary map. But it's very concrete element, right? It's not just element in K theory, it's a very concrete operator. Okay. And now on top of it, if we have a couple of elements in the ideal, we can use these elements to pair this element in K0 to something which is really in K1 of in K0 homology of ideal. So this is something in zero homology of ideal. So you pair those two. So you write down explicitly the pairing. So you should remember you have a projection, invertible projection. That's a, and then in a KK, you take to compute a pairing, you would take a trace. We don't take a trace. Instead, we take the determinant, okay, of this operator. This is Fredholm operator, and we take its determinant. And the delicate thing is really that. So first of all, this kind of everything's very non-canonical, right? So non-canonical in the sense that you have to pick up your represented projections, you have to pick up your representations, you have to pick up a concrete way of writing your Fredholm operator, and then you take its determinant. So it's there's nothing is invariant on the compact deformations, but it is actually invariant on the L1 deformations. So deforming things by trace class things does not change whatever we are doing here. That's why you get something. And since we know that the determinant, there's a canonical way of changing determinant when you do an L1 perturbation, this becomes well, functorial modulo L1 up to L1 perturbations. And that's why you can use it to define this cocycle.
Sorry for interrupting,
Yeah,
but
sure,
I have
go
a
ahead.
question related to precisely what you were explaining. So at the end, how much this cocycle, the cohomology class of this cocycle depends from these choices? Since, as you mentioned, you have many choices here possible.
No, there will be, could be quite different choices.
And then cohomology.
No, wait a minute. So what I'm saying, that's, no, I don't have much choices. I have these conditions here. So there's this bipolarization really, well, it's written down there, but this bipolarization really, it's things which satisfy these properties. And L1 deformations do not change that. So maybe I should explain how you get it. No, I don't think I wrote it, right? So, no, I didn't write it. No.
Yes,
No, it's a given the bipolarization, there is no choice. And this bipolarization, you can deform your P and Q, your P idempotents, up to L1, up to kind of joint L1 perturbation. The cocycle will be, the class of a cocycle will be the same.
So once the bipolarization is chosen, the rest of this construction.
The rest is automatic.
Fixed.
Yeah, it's fixed.
Okay.
No, the rest is automatic. And it's independent on the kind of L1 deformation of bipolarization.
Okay. And if you change this bipolarization, you can get at the end some different cohomology class, yes? Is it possible?
It's quite, if I change it completely, yes, it's quite possible. Okay. Of course, the problem is that you want a bipolarization which has nice properties with respect to infinity of the two torus. It's kind of restrictive. Okay, that's not that easy, right? So you need these commutators, products of commutators to be L1. But so you can do, you can basically the only freedom you have is action of SL to Z, I think.
Okay, but without this condition, do you think that it would be possible to classify all possible cohomology classes which can be obtained from this construction, the range of this map?
And the classes on what? Right?
The cohomology class.
No, but so there's one more thing which is not obvious here, which makes life more difficult. I'll read it here. So in this one-dimensional case, there's actually unique choice. given polarization, you have your group of general linear restricted group. Okay, and the cocycle is defined on the general linear restricted group. Given projections, this one projection, the rest is unique. So anytime you have a map of algebra into the group algebra of the general linear restricted group, you get a cocycle, and this is your universal extension, which shows up everywhere. So given polarization, the group is given. Here it's different. Given two polarizations, sorry, this bipolarization, the group is not given because there is this condition which okay, it's not quite visible from here, but it's this condition is not what's what? It does not define the group uniquely. It's condition of pairs of group. It's not condition of group elements. It's condition on pairs of group elements. And this condition is not closed under products. Okay, so it's a two extension, but it's a two extension for lots of different groups. It's not universal in this sense. Okay, so it does answer your question that there are lots of cocycles, right? But cocycles on different groups. Okay. So you pick up even or think differently, even given your P and Q fixed, you would get cocycles on you would choose different groups, different subgroup of GL, which satisfy our conditions, and you would get three cocycles on these subgroups. But the groups would be different in general, really different. Okay. So it's already more delicate than in the case of a torus. And maybe it explains why I have no idea what to do if in the higher dimension. Okay, because already here what I'm doing is I'm writing down explicitly Fredholm operator which implements Kasparov pairing between K-theory and K-homology. I don't know what to do in the higher dimensions. I don't have this higher type things, at least not at the moment.
The step involving this construction of a higher category would be most difficult, yes, but the definition of some kind of N polarization is accessible, or even
no, N polarization is straightforward. That's not a problem.
Okay. But the construction of the categories.
But construction of a category already starts to be a problem.
I see.
The problem is construction of a category. And polarization actually it's kind of generalizing these n-tate spaces. Okay, so this n polarization is think of Laurent series in n variables. And your projections would be, you would have n projections which correspond to removing negative powers in one of those variables. Okay, these are your n projections. And that's really your n polarization. Actually, really products of it, but that's good enough. And that's really what happens with in this algebraic case. When you use residue to compute to define functional and algebraic K-theory. Right, so the polarization itself is not a problem. Problem is defining a category in the analytic case, not algebraic, not from a power series, but analytic case. And seriously, I have no idea where to start. Maybe some kind of well, there is some kind of notion of Fredholm complexes, but it's not. But I don't know. I don't know how to start, unfortunately. So I need something that replaces this determinant of Fredholm operator as something higher. So some kind of instead of determinant should be some kind of Morita equivalence between some categories. Actually, it's kind of general problem. So It's very easy to define category. It's already very hard to define two category. And three categories and higher are, except for the trivial examples, they are not there. Okay. So it's in general, higher categories are not really something. You have topological definition, and then you can think about Kant complex whose homotopes vanishes for higher degree. This would be your higher. This would be your, apropos what you were saying, this would be your classifying space of your higher category. But it kind of feels wrong. Okay? It feels like it's a wrong construction. So three categories should, even though in algebraic context, should have some analytic element which is missing from topological construction. Well, but what it is, I have no idea. It's just a feeling.
Okay, Adam, so now let's move to Tomek.
Yeah, so let me start from a comment about the last explanation by Richard. To Adam, if you want to speak about higher categories for small levels of this higher category theory, you have some intuitions about topological combinatorial models of these categories. But if you want to go higher in these top categorical dimensions, you have many different models, like cubical, like globular, like simplicial, and it's not clear what choice would be best for your situation.
Sorry,
problem.
Sorry, when you are saying higher, you mean up from which end? Two categories already higher?
Starting from three categories, they start to diverge. Although there are some conjectures about equivalence of all these categories, higher categories, models. But to say what do you mean by equivalence becomes a part of higher category theory, and this becomes very quickly a mess. So maybe cubical models would fit to these problems, because your residues you are computing, they are computed like integration over some cubes and faces of cubes. So this is to Richard. In your conjectural formula with double residues.
No, wait a minute. So yes,
you have a integration over a cube, over a square, integration over some sides of this square, and evaluation at some vertices. So this suggests some cubical structure behind this.
No, it's not. No, it's because the formula looks at the way it looks. It's a bit different. So it's a Bedinson's regulator. So you look at the. Essentially, you look at analytic variety, and there is you can define a functional on algebraic K theory. So given f1, f2, up to fn, there is this higher logarithm, so f1 log f2 log blah, blah, log fn, and this has, if you are dimension n, this has a residue, or a shear residue, something like this. It's an n form on complex and manifold that has a residue. So you compute this residue, and that's the formula. But this is very much analytic manifold computation, right? It's real analytic functions. That's where formula comes from.
Yeah.
Well, what's missing? No, wait. So what's missing is something else. So these cocycles, they come kind of naturally. So for this one cocycle comes naturally from this category. It's actually, how shall I say that? it's really, you really define some multiplicative cohomology theory. So, well, let me try to share something else. Okay. Share. Let me find the picture. Yeah. So the way you construct a one cocycle, so you have your object and the group X. So there's an object, the group X gives you another object, and it's connected categories. You can pick up a morphism, right? From here to here, from here to here. And then you can pick up a morphism from here to here. And then since for each G, we picked up alpha G, we already picked up a morphism from here to here. Okay. Now we pick them up. Now the triangle here, so the two ways of going from here to here are not the same. They differ. They differ by an automorphism of a corresponding object, and that's your cocycle. And having a cocycle just means that if you, well, it's invariant on the triangulations. Okay. Now, in the case, in this one dimension higher case, well, what you get is analog picture, except corresponding to so this one corresponds to invariance of surfaces. So this really, in general, if you use it in topology, it computes Euler characteristic of a surface. Okay.
So this
picture
two cocycle comes from a two arrow.
No, yeah, from two arrow. Yeah. Well, it's from two no. Yeah, the way you can actually this two cocycle does not come from two arrow. This just comes from this picture here, right? Here. This cocycle, one cocycle comes just from composition here. It's one way going from here to here to here, and one way going here to here. The cocycle in higher dimension, you are right, comes from a two arrow. That's a two arrow. Now we are in one higher dimension. So we have one arrow, so this from X to G to G1X. And this have another arrow from here to here and then to here. So we have two arrows from X to G to G1X. And well, it's supposed to be two categories. So there is a two arrow going from this one to the composition of those two morphisms, alpha G1 and G2 alpha G2. So there is this two arrow.
Yeah, if I understand this, so right. If you think about the cohomology with values in some multiplicative theory,
yeah,
then you can define the coboundary. And this coboundary is twisted by this, so this, in a sense, this difference between left and right hand side of
no, don't think about that one. No, there will be multiplicative K theory, but it's not a question of coboundary. No, it's simply I have two different morphisms. So remember, I made choices. I chose a morphism from X to G2X. I made a choice of morphism from X to G1X. Okay. Yeah. But this means that I have automatically morphism from here to here. Okay, just applying G2 to it. Applying G2 to morphism from X to G1 of X, I get a morphism from here to here, right?
Okay.
So if I pick up morphisms which exist because I've got a connected category, then I get two different ways of going from here to here, right? So I can go this way, and I can also go this way, right? So I have two different morphisms. Well, in general, there are just two different morphisms, but in general, it's a two category. So I can pick up a two morphism which goes from one to the other, to the composition of those two. Okay?
Yeah.
It's a two morphism which goes from this one to the composition of, sorry, can't really do it, composition of this and this, right? So that's what I can choose. I have two categories. I can make these choices. Yeah, I can choose this alpha G2 and I could choose this beta G1, G2. Choose them arbitrarily. There's nothing canonical about them. But now what's happening is now you look at the tetrahedron, just as before, on the triangle, And now there are two different ways of going from here to here. Okay. So one way is, I think, here, here, and
More than two.
More than two, yes, exactly.
there are lots, but there are no. Essentially, there are only two different ways, right? So first, that's one way is going from here directly here. Sorry, this dotted arrow from here to here, right? Another one is to do trip abroad, right? X1 to G1X to G1, G2X and G1, G2, G3X. Okay. Now, for each of these triangles, we have chosen these betas. So composition of these betas, you have to be careful, but composition of these betas give an automorphism actually composition of these betas give automorphism of this morphism. Yeah, if you are careful, so this of this morphism. And now the conditions are saying that automorphism of this two morphisms, sorry, of one morphisms are invertible elements in my rank. So that's my cocycle. And the cocycle condition is, again, take these two triangles, glue them together, sorry, two tetrahedra like this, so, and another one below, glue them together, and then now you can cut it, either you can cut it as it's here over the common surface, or you can go from one top, you can draw a line from one top to another, and then you get three tetrahedra instead of two. And the cocycle condition says that independently of which way you triangulate this thing, the products give you the same number. So that's this topological property. We are still in topology. So it's really these cocycles give you invariance of, you should think of them as giving invariance of three manifolds, for example. And that's actually where they come from. Now you can try to construct invariance of four manifolds and higher, but there are no interesting invariants anymore. So you in topology, you do the same thing with three category. When we have four manifolds, you take with four category, you have five manifolds, and so on and so on. But there are no real invariants for already four manifolds. Have basically only the L invariant. So you look at the fundamental, you look at H2 and two homology, and there is a, and then you take the pairing of two homology with self-oriented four manifold. You can integrate that, and that's the only and that's pairing is the only interesting invariant. So there are no interesting invariants. So you need different structures to get something interesting. Okay. For three manifolds, we know that this gives a lot of information. For four manifolds, if you want something interesting, you really need different structures. That's what it's saying, that this finding this really interesting free category or something which works analytically, it's not obvious. Okay. Mm-hmm. Well, that's all I can say. I can't help really anymore.
Okay, guys, I think it's good time to wind it up.
Yep.
We are already like over half an hour above the allocated time. So unless there are some really emergency questions, I don't see any raised hands anymore. So Richard, also thank you very much for joining the chorus with Jens Kolb.
Welcome.
And till next time, we have Evgenis Kakariadis, I think, from Newcastle. Mm-hmm. So thank you so much, and see you in a week. Thank you. I stop recording. Bye bye.
See you.
Thank you.